Hi everyone, so here in this lesson we're going to talk about the best lab ever, which is the flame test lab. You'll need your notes and your periodic table, and you'll also want to make sure you can reference your lab notebook as well. So pretty much you're going to figure out how colors of fireworks are made. So why you have all those beautiful different colors there. So before we even talk about that, we have to talk about color and light and what that all means. So here on the left-hand side we have a light bulb. It's being shown through a prism. And the prism actually breaks up that white light into several different colors. And so first we have red, orange, yellow, greens, blues, and violets. If you notice, they all end up having the same speed, which is 3.00 times 10 to the 8th meters per second. You'll definitely need that in physics. And what the difference, though, is the energy versus the wavelength. The energy is measured in joules, and all of these numbers are times 10 to the negative 21. So it's really small when we can think about this. So anything that is in the reds will actually have a smaller amount of energy that, have a smaller amount of energy than any of those violets. The wavelength is different though. So the wavelength, those reds actually end up having a larger wavelength, and that actually represents, so like light travels in waves, right? So we have the distance from one wave till the other wave passes through. So the wavelength is much larger. So a red versus a purple can be shown like this. So the red wavelength is much larger than that of a purple one, or a violet one, excuse me. So whenever we think about police cars, for example, if you notice that they actually have red and blue lights, the red is because of the wavelength. It has a larger wavelength. The blue is because it has a higher energy. So you've probably seen the electromagnetic spectrum. I just want to show you this one example I found online. So the first section up here shows what can penetrate through the atmosphere. The next one shows you the different types of wavelengths and what that scale means to us, the frequency, and then the temperature. So there's a whole bunch of different things going on in here. I just want to show you. So radio, we have radio versus gamma rays. Gamma rays we'll talk about, or we have talked about in nuclear equations. So radio wavelengths are much larger than those of gamma. So if you notice, the wavelengths here are much larger than the ones over here. If we think about it in terms of the size, a radio wavelength is pretty much the size of a building. A microwave is between the size of a human and a butterfly. I know it seems pretty weird, but they can vary. Infrared is a needle point, so if you think about a little needle, sewing needle, that's the size of an infrared wavelength. The visible light spectrum are pretty much protozoans. We can see that with our unaided eye. Ultraviolet wavelengths, however, are the size of the molecules. X-rays are size of atoms, and gamma rays have the wavelength of the nuclei of an atom. This one little section right over here with the frequency, that is what we see as the visible light spectrum. So all of the colors that we see are just in this little area right here. Alright, and each element actually ends up producing its own spectrum, or its own bright line spectrum. So here, for example, the top one, we have mercury. So mercury will see some colors over here, two bands here between 4,000 and 4,500. We see a band of green right over here near 5,500. Three bands of yellow, a band of orange, and a small little band in the red section. Lithium, however, is a little different. We have two bands in the blues, one in the yellow, and one in the reds. Cadmium, again, a little different, two in the blues that are a little bit closer together, one in the green, one in the yellow, one in the orangish red section, and so on. So anytime you pass, you can actually look through metals through this bright line spectrum. So you'll see diagrams like this, and actually this will show you how each element does have its own different spectrum of color. So what does that all mean? That kind of comes down to our flame tests. So flame tests are when we took those metal ions and put them in fire, and from there we could see the different colors. So each metal ion will actually produce its own different color. Lithium should be in the red, Sodium should be one of the oranges. Potassium will be like a violet. Let's see, strontium was that beautiful bright red color. Barium was green. And lead, we kind of saw some sparks with those as well. So every element produces a different flame test, or every metal produces a different flame test color. And that can help you determine what a metal ion would be, what the identity of it would be. So this is what happens. Electrons will actually absorb energy and then move from the ground state to the excited state. So here we have potassium. Let's fill in those electrons, and the one little valence electron. What ends up happening is that that valence electron will actually end up moving up another energy level. So once we add in energy, it moves up another energy level. So the regular ground state, we call them ground state, like the normal state, configuration was supposed to be 2881. Now, the excited state was 28801. Most of the time you'll see one of the other electrons move up, so we could also have 287-1 or 287- make sure we have enough electrons here. Actually, this can be a 6 and then 1, 1. So it just depends on where those electrons are. Actually, that was supposed to be a 1. That would be a 2. That would be a 7. And at any rate, we want to show that we still have the same number of electrons. The number of electrons do not change, but their location changes. And again, the reason that happens is because they've been hit with the amount of energy. So in the case of the flame test, they've been hit with heat energy. So what happens with the color is when we actually end up having that one electron move down, back down to its ground state, and they actually will release energy in the form of light. So here are some questions that you'll see. For example, 1, many advertising signs depend on the production of light emissions from gas-filled glass tubes that are subjected to a high voltage source. When light emissions are passed through a spectroscope, bright line spectra are produced. So if you notice, this is really similar to the emission spectra I just showed you, but just not filled in with color. It's all black and white. So what I want you to do is think about this as you would a gel electrophoresis back in bio. I want you to line up all of these. So in gel electrophoresis, we looked at the unknown and compared it to known samples. Well, here's our unknown, and these are our known samples. So what we'll end up doing is showing that we can actually, we want to line up these bands, right? So here's a band there and there, a band there, there, and nowhere else in there, a band there and there, and keep going, all right? So you'll find that some may share more than one band, and that's okay. There and there. So if you notice, I've colored in any of the bands that are similar. So gas A and gas D are both fully colored in. All of their bands are colored in to match up with the unknown mixture. So the unknown mixture is comprised of gas A and gas D. Alright, the other type of question, explain in terms of excited state, energy transfer, and ground state. So whenever you see in terms of, I want you to underline that, box in anything that they want you to talk about. So they want you to talk about excited state, energy transfer, and ground state, how the bright line spectra is produced. So we want to know what happens or why that energy is being produced in the form of light. So really all we need to say is that when electrons move from the excited state to the ground state, energy is produced. Alright, so this little statement right here shows that we talked about the excited state, good, the ground state, and then the energy transfer, so energy being produced or released or anything like that. This is a really important statement I want you to memorize. In fact, I'll quiz you all throughout the year, and you'll be annoyed by it, but it really helps when it comes to the regions, and you'll be happy that you memorized it now. Alright, so to summarize, electrons gain energy and move from the ground state to the excited state, and then when they come back down to the ground state, they release energy in the form of light. So remember, these are the two statements I want you to memorize and understand what's actually happening with them. Alright guys, I will see you later. Have a great day.